Okay, good day and welcome to our lecture, data analysis. Data analysis is a very, very important topic in physics and also in pure mathematics. Now, why do data analysis? Of course, in mathematics, it can be about 10 marks. It's a 10-mark question that usually comes. And in physics, we can have, it's a 20-mark question. Okay, and it is very, very obligatory for you to answer it at the GCE. It is an obligatory question. 30 minutes, it is 20 marks. If you don't answer it, of course, you're going to lose the 20 marks. It is not a choice for you to answer it. You have to answer it. Okay, so that's why I committed myself to make sure that I give you a video on data analysis, because we'll be using one stone to shoot two birds. Now, what is data analysis? Data analysis is simply getting the relationship between two or more quantities, or let's say two quantities, using graphs. Okay, and now or you can also talk about establishing maybe a relationship between quantities, all right, using graphs. At first, you should have two sections. So in the beginning, when data analysis started coming in your GCE advanced level exams, they will give you a graph or maybe some data, and then you have to provide two graphs. The first part was usually to plot a raw graph, okay, just using the data you have been given. And then the second one was to plot a suitable straight line graph, and that was 1 hour. But now, since the time has also been reduced from 1 hour to 30 minutes, they no longer give the first part. You might encounter the first part in your experiments in the physics lab. So in the physics lab, you have to plot, get your data, then you plot a raw graph, and from there they can now ask you to establish a relationship and plot a straight line graph. But since the time has been reduced, you simply have just a second part where you are being given data and then asked to plot a straight line graph simply. Okay, you just simply plot a straight line graph. Now, in this first part of the video, I will try to explain to you how to analyze. How do we do analysis? Maybe I will give you different types of equations with the different kinds of analysis that you can be able to give, and I will give you the statements and the steps which you need to plot, okay, or what you need in order to plot a graph perfectly. So let's go. It's physics and math. Okay, and here we're talking about data analysis. Data analysis. Now, when you're being given data in order for you to analyze, okay, when you're being given data for you to analyze, you always start with what we call analysis. That's the first step. Please, you note it down. One is analysis. All right, followed by two, the statement of plot. Okay, statement of plot. What are you plotting against what, and how is the plot going to look like? What is it going to give? Okay, and then the third part is to establish your table, and then the last part, of course, you are supposed to plot your graph. And then that is all you are supposed to do for the graph part. But after the graph part, there is another part that follows for you to calculate the gradient. At advanced level, please, you always calculate the intercept. Number 6 is the intercept. You learn how to calculate the intercept, because if you try to plot a graph at advanced level, just starting your graph from zero, as we are going to see in subsequent lectures, it is not probably going to give you a very good graph. Sometimes your graph can be hanging. Now, we could accept that in Form 5, but we cannot accept that, or let's say ordinary level, but we could not accept that at advanced level for you. So your graph has to be very perfect, covering at least 3/4 of the graph paper, and of course your triangle which you are going to use to calculate the gradient should also cover at least 3/4 of the graph itself. So what we are going to do is, I'm going to start with analysis, and I'll teach you how to analyze different equations, because you analyze equations depending on what you have been given. All right, then I will give you some examples of analysis in math, and I will give you some analysis in physics. Okay, so please take notes. You do analysis first, You give your statement of plot. This one usually 3 marks. This one can be 3 marks, can be 2 marks or 1 mark, depending on the level to which your analysis goes to. If your analysis is long, then you have more marks. Then statement of plot. For the statement of plot, you need to give what you are plotting against, and this one is 2 marks, is constant. Okay, for your table, sometimes it has a mark. It depends on what you're, because sometimes you just need to draw by the table that I'm giving you in the equation. You don't need any other extra information. Then for the plotting of the graph, of course, and the other ones, we are going to see how the marks are being distributed. Okay. Good. For the first one, I'm going to start with analysis. How do you analyze the equation? Now, for you to analysis, you make your equation to be of the form y equal to mx plus c. So you make your equation to be of this form. In this form, y equal to mx plus c. That is the general form for the straight line equation of a graph. Okay, straight line equation of a graph. This is y equal to mx plus c. Y, of course, is the ordinate, all right, and I think x is the abscissa. Then we have our m being the gradient. Okay, our m here is the gradient, and then our c is the y-intercept. That's the vertical intercept where the curve touches the y-axis. All right. Now, if you have an equation of the form y equal to mx, all right, mx, just like that, it means that c is actually 0. So this kind of graph goes through the origin. Okay, this kind of graph goes through the origin. So we are going to be seeing the different kinds of graphs. So our goal during analysis here is to make our equation be in the form y equal to mx plus c. Okay. So what is an example of an equation that we can be able to have? All right, we can be able to have, for example, an equation. Let's say E equal to let's say, or let me use this other equation. Let's say now let's look at the energy. Okay, let's look at the maximum kinetic energy, or let's say the total energy which is being given to let's say the total energy which is being given by a radiation, particular radiation to a metal surface that's under photo emission. All right, that's a very good example for us to use. Okay, so when you give that total energy, of course, that total energy which you give is being used. Part of the energy is being used as the work function of the metal. Work function, some books use W and others use phi. Okay, we are going to be using W as a work function, and part of that energy is used to provide for the maximum kinetic energy, Ke max, which we call sometimes some books called C. All right, Ke max for the particle. But now in real terms, we are going to write this equation as hf. Okay, where f is the frequency. All right, f is the frequency of the radiation which you incident on the metal surface. Okay, and h is the Planck constant, equal to hf naught. All right, plus the maximum kinetic energy, Ke max. Now, if you follow some of the equations, I think it's the theorem of 2018, you're going to see some questions there. Now, they will give you the frequency. They will give you the frequency of the radiation, the frequency of the radiation which you incident on the metal surface, and then you'll be given the work function. You simply be given the work function W. Okay, maybe or phi. So the equation was given in the form HF. All right, just to make you get the sense out of this. So you have HF equal to W, okay, plus Ke max. So plus Ke max. All right. So you are being given the frequency, and maybe if you are given the kinetic energy, what you have to do is you have to arrange the equation in a particular form, in the form y equal to mx plus c. Now, if you want to plot the equation, you can analyze it in this form. This is going to imply that f will be equal to maybe say w over h, since h is a constant, plus if you are plotting the equation against let's say frequency against the Ke max, you're going to have Ke max. Okay, and this would imply that Ke max on H, implying that F will be equal to Ke max. We can write it as 1 over F times the Ke max plus W on H. Okay, because what function is a constant, H is a constant. Alright, this is called Planck's constant, and 6.64 times 10 to the negative 34 joules seconds. Now, if we have that, then we can now see that this one is like our Y. Okay, this is like our M, and here we are going to have our X, and this is our C. So, if you are analyzing such, if you had such equations and you were given frequency on a table, and you were also given the kinetic energy on a table, so it means that you can plot the graph of frequency against the kinetic energy. So I'm going to analyze the equation in this form and say, okay, a graph, you see, it is in the form y equal to ms plus c. So I can say, now my statement of plot, because here, each time I do analysis, I must give you the statement of what you're going to be plotting. So here, you can say frequency, a graph of frequency against Ke max, okay, a graph of frequency against Ke max is a straight line graph with gradient 1 over, sorry, this was 1 over h, okay, with gradient 1 over h and y-intercept w on h. It's simple, alright? A graph of frequency against Ke max is a straight line graph. Remember, this is a general equation for the equation of a straight line. So you have f, graph of f against Ke max is a straight line graph with gradient 1 over h and y-intercept w on h. Okay, so that is that is going to be the statement of what you're going to be plotting, and that is simply how you analyze that graph. Okay, now I'll use another example. I'll use another example of what you're supposed to plot. Okay. Okay. Now, what we are going to do is, let's use another example. Alright, let's use another example. Let's say, for example, I think June 2017, if not 18, where you were given the equation for a graph, or the EMF. The EMF for a battery is given as V plus IR. Okay, V plus IR. And you are given a table of V. Please, you always go to the table of what you have to know what to plot. So you are given a table of V. So your EMF was actually E. Okay, this symbol V plus IR in that manner. Now you are given a table of V and current, and so we are asked to plot a suitable graph. Okay, we are asked to plot a suitable graph from which you can be able to determine the values of R and E. So here, this will simply imply that I'll simply do an arrangement, alright, to look in the form y equal to mx plus c. That's all, alright. And what I do is I make v the subject of the formula, and v will be equal to if I make v the subject of the formula, e will be e minus ir. Okay, and since I know that I have a table of v and I, okay, I'll know what to plot. So v will be equal to negative r times I plus E. Okay, and from here, this is my y, this is my x. Okay, negative r is going to be my m, and E here is going to be my y-intercept. So what happens is that I will say a graph of V. All right, please, you go to that year, either 2017 or 2018. You check it out. A graph of V against I, a graph of voltage or PD against current, is a straight line graph with gradient negative m. Alright, that's the statement of what you are plotting. With gradient negative m and y-intercept E. Okay? A graph of V against I is a straight line graph with gradient negative r and y-intercept E. Okay? That is the statement of what you're going to be plotting, and that is all about this kind of analysis. That is all about the analysis for this equation. Now, in 2016, we have Please, at any point you can be able to pause the video and you get the information that we just put on the board and you can copy. Alright. In 2016 we had a graph. You were given an equation f equal to cure 1, okay, cure squared over 4 pi epsilon 0 r squared, okay, f equal to cure squared over 4 pi epsilon 0 r squared. This is a graph of what we're given. So we're given a table of f and r. Okay, we're given a table of f and r. Now there are other ways you could still analyze this equation. All right, you could still analyze this equation in several ways. Now this will imply that if I want to analyze to look in the form y equal to ms plus c, I could simply just take f equal to, since cure, which is a constant, alright, I told in the equation that cure is a constant, you have been given a table of f and r, okay? So I can decide to plot the graph of f and make cure squared over 4 pi epsilon 0, okay, times 1 over r squared, alright? So I am going to say this one is simply of the form y equal to mx, where cure squared over 4 pi epsilon 0 is my gradient and 1 over r squared is my x. So I will say a graph of f against, please not against r squared, a graph of f against 1 over r squared, that's why it's going to give a straight line. So all of this like that is your x. So a graph of f against 1 over r squared is a straight line graph with gradient cure squared over 4 pi epsilon 0 and passing through the origin. Why is it passing through the origin? Because the intercept here is 0. Okay, the intercept here is 0, so it does not actually it does not actually cut the y-axis at any other point apart from the origin. So it goes through the origin actually. Okay, so that's what you're going to see. Or I could still decide to say I'm going to be plotting a graph of r squared against f. So I could still arrange the equation. Now this is just one form of analysis. Another person might decide to plot a graph of okay, if I make r squared the subject of the formula here, I'll have r squared equal to cure squared over 4 pi epsilon 0 f. Okay, implying that r squared equal to cure squared over 4 pi epsilon 0. So I could rearrange it times 1 over f. So please, I could say a graph of r squared against f, a graph of r squared against f is a straight line graph through the origin with gradient cure squared over 4 pi epsilon 0. Okay, so so a graph of r squared against 1 over f, please, a graph of r squared against 1 over f is a straight line graph with gradient cure squared over 4 pi epsilon 0. Okay, just by making f here the subject of the formula. So I could be able to give you like this, or I could be able to give you like this. Either way, so your graph is going to give you a straight line. Is going to give you a straight line. Okay, your graph is going to give you a straight line in either ways. Now, that is it. All right, for this kind of graphs, you just simply do some rearrangements and you get it right. But there are others that you have to step up a little bit, okay, to apply some stuff. Now, if I have a graph, for example, they tell you that the energy per unit area of the energy varies in the form of a capital T to the power n. Okay, this is how the energy varies. I think this is from Northwest Smoke 2013. Now, if we have this, the only way I can be able to bring down this power is either to apply log or to apply ln. Now, in physics, most of the times we prefer to use ln. I don't know why, but you could still use your log. Okay, or because the graph is giving your hands, you are not told what to do. Sometimes in maths you are told what to plot against what, but here you don't. You are not being told what to do, so you are the one that knows how to analyze it. But it's very just use ln. That's what I'm supposed to use. So I bet at the end you're going to have the same answer. Okay. So here, for me to bring down this power, I have to apply logarithmic function. to this equation. So if I apply ln to both sides of this equation, I'm going to have that ln e will be given as ln a times ln c ln a t to the power n. But given that, okay, ln a plus ln ab is the same as ln a plus ln b. Alright, note that please ln a on b is the same as ln a minus ln b. Alright, and then ln a plus b is not the same as ln a plus ln b. Please take notes, because these are some very big blunders that students do. You when you have a plus here, you don't dare expand the bracket. If you expand the bracket, you fail it completely. So this is what you do, and then you have ln a to the power n is the same as n ln a. Okay, and if you have, let's say, ln e is equal to 1, right? Ln e is equal to 1. So we are going to be using that so often. Wherever you see ln e, you just replace it 1, okay? So here, let's say we are analyzing ln e is equal to ln at to the power n. Now, this will imply that ln e will be equal to ln a is a product plus ln c to the power n. So I can be able to arrange it as ln e equal to ln a plus n ln c. Alright? And then I could still be able to arrange it further as ln e equal to n ln c as n ln c plus ln a. Okay, I could be able to arrange as n ln c e equal to n ln c plus n ln a. Plus ln a. Now, why am I arranging like that? Because on the table, surely you're going to be given a table of E and T, where T is the absolute temperature. Alright, in this case, please, this particular equation, if you try to look at the question, you're going to be having T as the absolute temperature. Alright, and A will be a constant, N will be a constant, and E will be the energy. Now, don't worry, just learn how to analyze it. During the plotting of the curve, I am going to tell you more about it. I will surely come back to this part of the absolute temperature. Okay, so this is it, and we are plotting a graph. So a graph of ln e against ln t is going to be a straight line graph with gradient n and y-intercept ln a. Okay, let me take it again. A graph of ln e, that's the statement of what they are plotting, and that statement is very, very important. It's 2 marks. So if you miss it, you miss 2 marks. So a graph of ln e against ln t is a straight line graph with gradient n and y-intercept ln a. Because if you actually write, this one will be y, this one will be your x, this one will be m, and this one is going to be your c. Alright? And that is how you analyze such graphs when you see a power grid. Okay? So please just take a look at it, and then I am going to go to another, I'll take another form of an equation, and I'm going to analyze it for you. We'll analyze it together. Alright? Okay, cool. Okay, so please, that's how you analyze such graphs. When you see anything like e equal to 80 to the power n, that's what you're going to be doing. Alright, now let's try to analyze it again. Let's try to look for another equation which we are going to analyze, maybe using ln. Now in maths, I'll just give you an example maybe of an equation that is usually solved in maths that way. So here we're going to have, let's say, y. Some very common equations. So they will give you y equal to let's say x e to the x e to the a. Okay, x e to the a. All right. Okay. So we have y equal to xe to the a. Now if you are asked to plot a graph of such an equation, what are we going to do? What we are going to do is, you simply, of course, as I told you, when you see anything raised to the power, what you have to bring it down is a logarithmic function. So if you want to use ln, you can use ln, but in this case, let us use log. Alright? This implies that we can say, for us to analyze, you can say log y to the base 10 is the same as log of x e to the a. Remember, it's a product. And the same laws of ln that we just saw there also applies for log. All of them are logarithmic functions. The one is natural logarithms. So you have log y can be written as log x, okay, plus log x plus log e to the a, right? And of course, you can rewrite it as log y is equal to log of x, okay, log of x plus a log e, okay, a log e, or something like that. Now, of course, this one is simply just going to be if you're plotting a graph, you're going to say a graph of log y against log x is actually going to be a graph of log y against log x is going to be a straight line graph with gradient a log e and with gradient 1, and the gradient is going to be 1 and the intercept is going to be a log e. Alright, but that's not really a very perfect example for you. Okay, that's not really a very perfect example, but all is that you have learned how to analyze that particular equation. Okay, so you have learned how to analyze that particular equation. Now, what if maybe let's say we had something like